So today I want to talk about fractions and specifically raising fractions to high powers. So let's start with a couple of examples to get the intuition and then we'll prove something. So let's start with maybe the simplest fraction of all, half. And then let's consider what happens if I take half and I raise it to the power of 2, so squaring it. Well, that just means I square the top and I square the bottom. Oops. So that is 1 over 4. And this, of course, corresponds to the fact that if you start with half, and then you take half of a half, then you're down to a quarter. And similarly, if you take a half and cube it, then you get 1 cubed over 2 cubed, which is 1/8. And that corresponds to the fact that half of a half is an eighth, right? Because multiplication corresponds to this word of, right? Half of a half is a quarter, half of a half is an eighth. And so what we see here, if we look at this pattern, is we get a half, a quarter, an eighth, a 16th, a 32nd, and we can kind of see, at least intuitively, that these numbers are going down and down and down and down, and getting arbitrarily close to 0. Right? And that kind of makes sense. If I keep having something, cutting it into smaller and smaller slices, it's getting arbitrarily small. It's vanishingly small. Okay, so that's the deal with half. Let's look at one other fraction and then formulate a question. Let's look at a fraction like 4/5. Right? Perfectly simple fraction. It's more than a half. What happens when I take 4/5 and square it? Well, I get 16/25. This is 4/5 of 4/5. Okay, 16/25. Well, that's, not a fraction that you might normally think of, but you can kind of see it's, it's a bit more than 3/4, right? 3/4 would be, it's a bit more than 3/5 is what I mean. 3/5 would be 15 over 25. This is 16 over 25. It's a bit more than 3/5. What about if I cube it? 4 over 5 cubed, that's going to be 4 cubed over 5 cubed. That's going to be 64 over 125. Now I've got something which is close to a half, right? 64 times 2 is 128. So this is a bit more than a half, very close to a half. What about if I take 4/5 and raise it to the power of 4? Well, that's going to be 64 times 4 on the top, which is 256, and 125 times 5 on the bottom, which is 625. Now we see we're definitely less than a half, but greater than a third, right? Because if I multiply the top by 3, I get like 760 something. Let's do one more just for illustrating. What about 4/5 to the power of 5? Well, that's going to be 256 times 4, so that's going to be 1024 on the top, and on the bottom it's going to be 625 times 5, so that's going to be 3,125. And we can actually see this is just a little bit less than a third, actually. Right, the top times 3 is not quite 3,125. So what's happening, we started with a higher fraction, still less than 1, but a higher fraction. And as we square it, cube it, raise it to the power of 4, raise it to the power of 5, we're getting, again, smaller and smaller fractions. Now you might ask, and at least for me, I don't think it's obvious. It's obvious for a half that this process brings you closer and closer to 0, in the sense that it brings you arbitrarily close to 0. You get vanishingly small. But what about this process? Right? It clearly gets lower, right? Of course, every time you're taking 4/5 of the thing before, so it's getting lower. Is it going to get to 0, though? And by get to 0, I mean, does it get arbitrarily small? Or maybe it approaches 1/3. Maybe it never goes below 1/3, or maybe it never goes below 1/4 or 1/5. How would you know? So this is the question, now that I've motivated it, that I want to answer in this video. It's an elementary fact, and I'm going to give you an elementary proof of it. It might not be the simplest proof. I don't know what the simplest proof is, but it's an elementary proof. And here's the fact. if m and n are natural numbers, and we have n is bigger than m, which is bigger than 0, then the limit as k goes to infinity of m over n to the power of k equals 0. And this is just to say, if I take a fraction where the numerator is smaller than the denominator, which means that it's a fraction which is less than 1, and I raise it to the power k, then as the power k gets higher and higher, the fraction overall that I get by raising it to that power approaches 0. It gets arbitrarily close to 0. So it doesn't, reach some threshold and never go below that. It some positive threshold. It actually goes all the way down to 0. So what we'll actually prove is the following version of this. For every threshold m, there exists a k such that m over n to the k is less than 1 over m. If you go look at the video that I put out on defining limits, then you'll see the relationship between these two statements. This is sort of an expression of the idea of a limit. It's saying, look on the right-hand side, this is 1 over m, right? As m gets larger and larger, this becomes a smaller and smaller fraction. So what this is saying is that as long as I have this setup, m and n are natural numbers, and m is less than n, then there's always a high enough power that I can raise this fraction to get it to be smaller than 1 over m, no matter what n is. I can get it to be smaller than a quarter, smaller than a tenth, smaller than a billionth, right? Because it's true for every m. For every m, I can find a high enough power of k to get it to be that super small. So this is what we're going to prove. And in fact, equivalently, this is just a small algebraic manipulation, but maybe it's worth pointing out. This is the same as, of course, m to the k over n to the k is less than 1 over m, which is the same as doing some multiplication. This should be a capital M. N to the k over m to the k is greater than m. So if I multiply both sides by n to the k and both sides by m, and then divide both sides by m to the k, I get this expression, which is sort of like saying, it's exactly like saying, if I take the reciprocal of this fraction, it gets arbitrarily large, right? In other words, the ratio between n to the k and m to the k gets arbitrarily large, which is why the fraction of m to the k divided by n to the k gets arbitrarily small. So this is just going to be slightly easier to work with. Okay, so let me give myself some space. And I'll restate what we're actually going to prove up here. For every m, there exists a k such that n to the k divided by m to the k is greater than m. That's what we arrived at. If I've got these two numbers, I can always raise them to high enough power so that the ratio between them is as large as I want it to be. Now, how am I going to do this? Well, the elementary method is going to use the formula that generalizes difference of squares that I introduced in the previous video. So if you recall, we look at n to the k minus m to the k, the difference between these two powers for some k. I'm not saying what k is yet. And we saw in the previous video that this is equal to n minus m times a long expression, which is n to the k minus 1 plus n to the k minus 2 times m. And you continue this pattern all the way to n times m to the k minus 2 plus m to the k minus 1. Okay, so check out the previous video, which I've linked to, to see why this formula is true. It's a generalization of the difference of squares formula. So now this is the difference, not the ratio. We'll get to the ratio later. This is the difference between n to the k and m to the k for some fixed k. Now what do I know? Well, I know that n is greater than m, and these are natural numbers. So this difference here is at least 1. It might be 1, it might be 2, 3, 4, depending on how far apart n and m are. So that tells me that this thing here is at least n to the k minus 1 plus n to the k minus 2m, dot, 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 n m k minus 2 plus m k minus 1. Because the lowest this could possibly be is 1, in which case it's equal to this. And otherwise this is 2 or 3 or 4, so it's just making this top one bigger. So by ignoring this, I get something which is definitely no bigger. Now the next thing I can do is I can actually say, well, I know that n is bigger than m. By the way, to do this last step, it was important that this thing here is clearly some positive number, right? It's a bunch of powers, it's a sum of a bunch of powers of products of positive numbers. So now to do the next step, I look at this and I say, well, n is bigger than m, right? They're both integers, they're both natural numbers. N is bigger than m, so if I replace n by m, I'm only making the corresponding expression smaller. So this is strictly bigger than replacing n by m to the k minus 1. And here too, I'll replace n by m, and I get m to the k minus 2 times m. And here too, I get m times m to the k minus 2, m to the k minus 1. So replacing every instance of n with m is just giving me something strictly smaller, because m is strictly smaller than n. But now this is a convenient expression, because this is m to the k minus 1. This is m to the k minus 1, right? When you multiply, you add the exponents. This is an exponent of 1. So is this. And in general, all of these terms in the sum just simplify to m to the k minus 1. And there are how many? K of these. If you count these up, right, it goes from m to the k minus 1, k minus 2, all the way to m to the 0, so that in total there's k terms here, if you count them up. Which means this is just equal to k times m to the k minus 1. Right? It's that m to the k minus 1 added to itself k times. Now we're almost done. How are we going to make use of this? We can do it over here. Remember, we're allowed to choose little k. The point is that I want to show that I can always find a k which is big enough so that the corresponding ratio of n to the k over m to the k is bigger than m. So here's what I'm going to do. Choose k to be equal to m times m. Capital M being this ratio that I'm trying to get bigger than, and little m being the smaller of the two numbers that I'm raising to an exponent. Well, if k equals m, capital M times little m, then what we've figured out over here tells us that n to the k minus m to the k is strictly greater than k times m to the k minus 1, which is m times m to the k. This m multiplies by this m to the k minus 1 to give me m to the k. Now, therefore, if I divide both sides by m to the k, I get n to the k over m to the k minus m to the k over m to the k, which is 1, is greater than this divided by m to the k, which is m. So this minus 1 is greater than m, so clearly n to the k over m to the k is greater than m. And that's what I wanted to show. So there's a bit of algebra to do to figure it out, but by considering n to the k minus m to the k and factoring it using the generalization of the difference of squares and doing some inequality reasoning with that, we reached a point where we could choose a value for k, namely capital M times little m, which was so big that it guaranteed that the ratio between n to the k and m to the k was bigger than m. And that works for any m, so I can get this ratio to be as big as I want, which of course means I can get the reciprocal, m to the k divided by n to the k, to be as small as I want.